Hey guys, welcome to Unit 1B, Notes D. Today we're going to talk about empirical formulas and hydrates, which actually use empirical formulas as well. So just to remind you what an empirical formula is, basically the simplified version of a molecular formula. A molecular formula is going to tell you exactly how many of every type of atom are involved. Let's use a common example here with sugar, C6H12O6. So a real sugar molecule would have exactly 6 carbons and 6 oxygens, but 12 hydrogens. Now the empirical formula of sugar would be CH2O, showing there's twice as many hydrogens than there are carbon and oxygens. But that doesn't mean that sugar actually has 1 carbon, 2 hydrogens, and 2 oxygens. So when you're told it's the empirical formula, or when you intentionally find the empirical formula, you have to keep in mind all that you found is the ratio. Then we're going to use molar mass to compare the simplified version to maybe the molar mass of a real molecule to see what kind of multiplier we would need. In this case, a 6. We have 6 times as many atoms from our empirical formula to our molecular formula. A common way to actually be able to determine this experimentally, keeping in mind that IB has a heavy lab emphasis, is to actually look at some version of a decomposition or dehydration in terms of hydrates, some kind of chemical change where we're actually able to simplify and separate out in order to determine a ratio. So let's look at an example where that's the case. So first, let's identify numbers here. We have a 2.765 gram sample of lead oxide. 2.765 gram sample of lead oxide. Now I know the symbol for lead is Pb, and I know oxygen is O, but keep in mind that lead acts as a transition metal in terms of its charge. It could have various charges, so that makes it impossible to predict the actual subscripts here. We're going to have to go about that a different way. What it tells me here is this chemical reaction of this lead something, oxygen something, this lead oxide, was heated in a stream of hydrogen gas and completely converted. So there is actually a way to show that chemical reaction used a hydrogen catalyst without that being an actual participant in the chemical reaction. Not that that matters to this problem, just kind of wanted to show you what that looks like. So it's converted into completely experimental lead, so Pb, and we know that lead can exist alone. It's not diatomic, so we'll leave it like that. And there would obviously have to be some oxygen given off as well, which we know would be diatomic. What it gives me is the mass of the experimental lead. Now, it doesn't talk about the oxygen because it can get a little hinky if you start thinking about diatomic oxygen. What I can tell, because it isolates into solo lead, is however much lead this was, in this case 2.401 grams, that would be the same mass of lead in the end. And then it also had told me the sample of the entire compound was 2.765 grams. And so from that, using the idea of the law of conservation of mass, I can tell if the entire compound had 2.76 grams and the lead alone had 2.401 grams, then whatever other mass that's missing must be the oxygen that we ended up with the product. And it really doesn't matter to the empirical formula part of the question about whether that's diatomic or not in the end. So I'm kind of going to take a step back. I did want to show the equation in general, but this is really the part that matters here. I had a total mass of 2.76 grams and the lead is 2.40 grams. So if I find the difference, I can get my oxygen. And that would be 2.75, nope, so it's 2.765. Can't say that number for some reason. Minus 2.401, and we get a difference of 0.364 grams. So this was our total. We subtracted the lead, and we got the oxygen. But grams doesn't do us very much good when we're trying to look at a ratio. The only unit we can use for ratios is moles. Moles has a purpose, and that is to allow us to compare numbers. So we're going to use moles to compare. So now I have to do a gram to mole comparison, which should be no stranger to us at this point. So I'm just going to start with the 2.401 grams of lead, and I'll put grams of lead on the bottom, moles of lead on top. Remember, 1 mole is equal to the molar mass, and for lead that would be 207.19. I'm going to do the same thing for oxygen. 0.364 grams of oxygen, single atom oxygen as it was in the compound. It doesn't matter the product. I'm looking at how much regular just atom oxygen would be in the lead oxide. So then I have grams of oxygen on the bottom, moles of oxygen on top, 1 mole to the molar mass of a single atom of oxygen, which is 16. So now that I have my mole conversion set up, let's make some room here. I want to know how many moles of lead and then how many moles of oxygen. So I'm going to do 2.401 divided by 207.19, and I get 4 significant figures, 0.01159. Looking at my oxygen, I'm going to do 0.364 divided by 16 to 3 significant figures, 0.0228. Each of these being moles, but of a different substance. But now that I'm in moles, now I can make a mole ratio, comparing my moles of lead to my moles of oxygen. Whenever you make a mole ratio, you always want to divide by the smallest. We ideally want whole number mole ratios. So we want to look at big number divided by small number. So I've got 0.01 compared to 0.02. The 0.01 would be the smaller number, so I'm going to divide by my lead moles. Now, is it any surprise that moles of lead compared to moles of lead would be to 1-to-1 ratio? Of course, you're going to get that for one of them, whatever the smallest one is. So what is my ratio of oxygen to lead? So I'm going to type in, actually I still have it in my calculator, 0.02275, which I had rounded here to 3 sig figs, but that's okay. I'm going to go ahead and hit divided by 0.01159, and I get now, let me do it down here. I'm going to stick with the 3 sig figs though, 1.96, which is close enough. You want to be within a tenth to round to 2. Showing that I have just about twice as many moles to lead, which is why I wasn't super worried about the precision on our significant figures. So I have twice as much oxygen than I do lead. I'm going to represent that in my formula. Lead something to oxygen something. So if I have 1 lead, I would have 2 oxygens. Keeping in mind that this is just my empirical formula. How much lead oxide do I have? Well, twice as much oxygen would be present in that lead at a given time. That is my empirical formula. We're going to take a second to reset this up, and then we'll convert to molecular formula. There we go. So just a little recap, the mass loss must be oxygen. So we did our subtraction to get the mass of oxygen. We converted the mass of the lead with the molar mass, and then the mass of the oxygen with its molar mass. Once we got to the 2 moles, divide by the smallest, and we can finally get our empirical formula, the PbO2. But does that really mean that there is a molecule that has only 1 lead and 2 oxygens? Well, in order to determine that, we need to know what the molar mass is of the molecule that we're trying to identify. So if I add in that information, right now I'm looking for a molecule that actually has a molar mass, and look at the IB terminology here, M sub R for relative molar mass, relative atomic mass. So we've got a given mass of 717.6 grams per mole. So the question is, does my PbO2 fit that bill? Well, let's look at what the molar mass would be of just regular PbO2. So we would take our molar mass of the lead, 207.19, and then the oxygen twice at 16 once. Twice would be 32. And if we total that all up, we'll get the molar mass for just that one pairing, that one group. 207.19 plus 32. We get 239.19 in its molar mass, so it's grams per mole. Now, if just one lead and two oxygens has a molar mass of like 200, could it possibly be the answer to the true molecule with a molar mass of 717? No, definitely too small. But to go from empirical to molecular, we just need the multiplier. We know that this is the ratio. So is it twice this many, 3 times this many, 17 times this many? How do we figure out how many times more we have this set of atoms? So the easiest way to do that is actually to take the given mass, molar mass I should say, and divide it by the molar mass of your set of your empirical formula. So 717.60 divided by 239.19, 239.19, and I get about 3. So that means there are 3 times as many of this set, which we know equates to 1 lead and 2 oxygen, in order to get to 717. So that means I have to have 3 times as many leads, 1 becomes 3, and 3 times as many oxygens, so 2 becomes 6. 3 times as many stuff. So this would be my molecular formula, Pb3O6. Notice that it still has twice as many oxygens as lead, exactly what I showed in the empirical formula. So Pb3O6, final answer for our molecular formula, based on our multiplying factor compared to the empirical formula's molar mass in order to get the molar mass that's given. So Pb3O6. All right, so when we first talked about hydrates, it's kind of hard to think of them as empirical formulas, but they really are. For example, in this one, we're looking at a hydrated strontium hydroxide. So strontium hydroxide is going to have our, what is the symbol for strontium? SR, sorry. So we have SR and then hydroxide OH. Now strontium's in the second column on the periodic table, so it has a +2 charge. So we're going to balance our charges real quick. And then it says that it's hydrated, so I know it's attached to water molecules. And that was our basic setup for hydrates, right? But the thing is, we need to know how many waters compared to the anhydrate. This is very similar to finding the subscripts like we did in the last problem. Here I'm just looking for kind of like the coefficients in front of anhydrate versus water. How much water per anhydrate? So again, we're going to be driving towards a mole ratio, so we can compare one part of the molecule to another. So let's look at what information they give us about this hydrated strontium hydroxide. So it's strongly heated. Remember, with hydrates, we want to get it to a constant mass so we can determine the difference between the hydrate and the anhydrate. And what we're driving off in this heating process, or dehydration process, I should say, is the water. So this actually shows a decrease in mass of 54.2%. So what is being removed in order to decrease that mass? It must be the water. So I now can tell I have 54.2% water. And after reaching constant mass, after removing all of that water, what would be left is the anhydrate. So if I find the difference from 100, I can get the percentage of the anhydrate, or in this case, the strontium hydroxide. So 100 minus 54.2 is 45.8% strontium hydroxide. Okay, so what am I going to do from here? How am I going to move from a percentage to a mole ratio? fairly comfortable going from gram to mole, but now I'm stuck in percentages. So there's a trick whenever you're in percentage. The truth is, it really doesn't matter what the total mass is. Finding each percentage of whatever mass I make up is still going to get me the same mole ratio in the end. So what would be the easiest percentage to work with to go from percentage of some random number, find each percentage of that, and use grams that way? We'll just assume 100 grams. So that's a pretty cool trick whenever you're dealing with percentages. Basically, just treat them as if that is the grams. 54.2% of 100 grams would be 52.4 grams. 45.8% of 100 grams would be 45.8 grams. So treat your percentages as grams because you can just pretend that you're finding that percentage of 100. So now I need to start working towards my mole ratio when I'm stuck in grams. So the trick here, of course, is to use the molar mass to convert from gram to mole. So I'll start with the water, 54.2 grams of H2O over 1. And then I'll put the grams of H2O on the bottom, good old dimensional analysis, top to bottom, using my mole conversion here. And so I know 1 mole is equal to the molar mass, which for water is 18.02 grams. So how much, or how many moles, I should say, of water? 54.2 divided by 18.02. And I get to 3 significant figures, 3.01 moles of water. Now let's look at the strontium hydroxide. So that was the 45.8 grams of the SrOH2 over 1. Then I'll put the grams again on the bottom, gram of SrOH2 to moles of SrOH2. Watch your parentheses because it is 2 hydroxides, not just 2 hydrogens. 1 mole, and then now I need the molar mass of hydroxide. I should have looked at that earlier when I was kind of cheating. Let's see here. 121.64. I know that's hard to see. Let me go back. Here we go. So molar mass of 2 hydroxides plus a strontium would be 121.64. So now I'm going to take my 45.8 grams, which remember was the complement of what would be left at constant mass. So 45.8 grams of my anhydrate, and divide that by the molar mass of the anhydrate, 121.64. And to 3 sig figs, I get 0.377 moles of the SrOH2. So now that we have our moles, it's time to get our mole ratio, comparing moles of one thing to the other. Just like with empirical to molecular, or just like with finding the empirical, I should say, you always divide by the smallest. We want the whole numbers if we can. So big number 3, little number 0.3. I'm dividing by the 0.3. 0.377 moles. And of course, what would we expect comparing moles of something to itself? And a number divided by itself is, of course, 1. So I have a 1 mole to mole ratio of strontium hydroxide to strontium hydroxide. Big surprise there. Let's look at our mole ratio for our water. Calculator. 3.01 divided by 0.377. And we get to 3 sig figs, 7.98 moles of water per mole of strontium hydroxide. So this is telling me how much water would be attached to that anhydrate. And this is, again, close enough, within a tenth, to round. So we would say that that is approximately 8. And what we just solved for is actually the hydration number. How much water per anhydrate? How much water on that strontium hydroxide? So going back to the formula here, I almost forgot my parentheses. There we go. The goal was to find this mole ratio. How much anhydrate to how much water? Well, there's 1 strontium hydroxide for every 8 waters, 8 to 1 mole ratio. So this is strontium hydroxide octahydrate with 8 water molecules. it works exactly the same as finding the subscripts for an empirical formula. It all really comes down to finding a mole ratio. Convert grams to moles, divide by the smallest. So we had first to understand the percentages, which was a little bit of a complication on this one. When it says the mass is decreased by 54%, in a dehydration, that mass loss will always be water. So we're removing the hydrated part to get the strontium hydroxide alone. So then you can find the difference from the water and the 100% of the compound to get how much of the strontium hydroxide would be left. Then you can assume those percentages are of 100 and just start treating them as grams, using your molar mass to get into moles. Once you're in moles, you're in the home stretch. You're just going to divide by the smallest so you can get your ratio. 8-to-1 ratio, 8-to-1 ratio tells us how much water per anhydrate. All right, and that's going to do it for our notes on empirical formulas and hydrates, which, as we can now see, are a version of empirical formulas. Our next set of notes will be Unit 1B, Notes E, where we're going to talk about solutions. We'll see you there.